I just wanted to make a quick announcement. I think it works, right? Okay. The live streaming of the program starts at 6:30, so we're gonna start the live stream. Good evening. My name is Christina Aleki, and I'm the Executive Director for the Chicago Council on Science and Technology, and it's my pleasure to welcome everyone tonight. Sorry for the delay, but people are still coming into the building, finding 1871, so we delayed a little bit. Again, it's my pleasure to welcome you all who are here in the seats and also those who are watching online. We are live streaming the event. The Chicago Council on Science and Technology, or as we refer to it, C2ST, is a nonprofit organization that aims to enhance the public's understanding of science and technology and their impact on society. It's our hope that more people know about science and technology, the more intelligently they will vote, the more informed decisions they make in their lives. Over the last 9 years, we have produced 140 public programs, and our programs range, has a wide range of subjects such as cybersecurity, cancer research and prognosis, or physics of baseball, or for example, global climate change. When you come to our programs, you can be sure you will be receiving accurate and cutting-edge information from Chicago experts from the field. C2ST could have not made it this far without your help and without our members' support, our sponsors' support, and our friends. Tonight's program was produced in partnership with Argonne National Laboratory, and it's also sponsored by the Alvin H. Baum Family Fund, and we wanted to thank them for their generous support. I would also like to welcome a member from the Elizabeth Morse Genius Charitable Trust and say a big thank you for their support for our efforts. If you like tonight's program, please consider joining as a member or donating to our organization. You can do that either online, www.c2st.org, or flagging down one of our staff members. And before I introduce our speaker tonight, I would like to highlight 3 upcoming programs. On March 15th, C2ST will celebrate Brain Week. And the celebration will be a program, part of our C2ST Speakeasy series at Geek Bar Chicago. And the program will talk about or explore how sense and human behavior relates to each other. On March 23rd, C2ST will present the science of addiction. It's a very important topic, and we will present this with the Neuroscience Society of Chicago chapter at DePaul University. On March 31st, C2ST has partnered with the American Association of Women in Science for the national summit that will take place at the University of Chicago Gleacher Center, downtown Chicago. Also, save the date for Thursday, May 5th, for our annual fundraiser gala that will take place at UI Labs on Goose Island. As I mentioned, tonight's program is live streamed, but it's also recorded. So if any of your friends or colleagues miss tonight's program, please make sure that you tell them that it will be available on our YouTube channel, which is C2ST TV. Please use @C2ST #climate when you tweet about the program. And a little bit of house rules: please turn the volume down on your cell phones and keep your questions to the end of the talk. We have 2 handheld microphones, and staff members will pass around the microphones, so you will have a chance to ask questions. Usually we leave 20 minutes for a Q&A, it's important to say your questions in a microphone, or Seth, I would like to ask you to repeat the questions so those of who are following online can hear the questions as well. So tonight's presentation is a program in our Climate and Energy series, which is one of our most popular programs, as people are very hungry for science-based, evidence-based information when it comes to global climate change. And tonight's presentation will just do that. We'll focus on science-based evidence of climate disruption and lay out the options available to us to a secure and more sustainable future. And with that, I would like to introduce our speaker, Dr. Seth Darling. who will also be featured on WTTW Tonight, Chicago Tonight on April 6th in relation to this program at the 7 to 8 o'clock segment. Dr. Darling is a scientist at Argonne National Laboratory and a fellow at the Institute for Molecular Engineering at the University of Chicago. His group's research is motivated by humankind's grand challenges and centers around molecular engineering with a particular emphasis on solar energy and water treatment. Dr. Darling has published over 100 papers and a very popular book on climate change, How to Change Minds About Our Changing Climate. And he told me that he has a few copies today available to buy. It's $15, but he can only accept checks. No, cash, sorry. Cash. Checks are fine too. Dr. Darling has also holds several patents, gives lectures widely on topics related to energy, climate, and water. And with that, Dr. Darling, the stage is yours.
Thanks for the kind introduction. Is my mic on? Sounds like it is. Good evening, everybody. Thanks for Can you hear me now? The Verizon ad. How about that? No? Do you want me to use a handheld? Okay. Technical difficulties. So thank you all for coming out. There it is. Jeez, I'm really loud. Okay. Thank you all for coming out. It's beautiful weather outside, and I know I'd probably rather be outside myself than in here listening to me. Okay, so I'm going to tell you about climate change, or as I like to call it, climate disruption. But let me take a step back and tell you why we're all interested in this. So the gentleman pictured on the side of the screen here was Rick Smalley. He won a Nobel Prize in chemistry. But the reason I have him up here is because in the later years of his life, he devoted his attention to identifying the top 10 challenges that we face as a society over the next 50 years. And he has them in order from top to bottom. It doesn't mean that the challenges at the top are more important than the challenges at the bottom, but if you can solve the challenges at the top, it helps you solve the ones at the bottom. So one example, you notice population is down there at number 10. We have unsustainable population growth on this planet. But it's been well established that if you improve education in the developing world, particularly among women, birth rates will go down. That helps you solve the population problem. So if you fix education, it helps you fix the population problem. And you'll notice all the way at the top of the list is energy. So at least according to Rick Smalley's analysis, this is the biggest challenge that we face over the next 50 years. To give you one more connection, you'll notice number 2 on the list is water. We don't have a shortage of water on Earth. There's quite a lot of it, but we have a shortage of fresh water, and it is becoming an increasing crisis, in fact. We know how to take seawater and to make it into fresh water, desalination, but to do so takes a lot of energy. So if you solve the energy problem, it helps you solve the water problem and so on. So why is energy the biggest challenge that we face? I can sum it up in this one slide here. This is a plot of how much energy we use worldwide by year. And the units that I'm going to use are terawatts. That's 1 trillion watts. So it's a lot of energy. You can picture, a light bulb in your ceiling is 25 watts or so. Here we're talking about trillions of watts. And you can see that every year we use more energy than we were using the year before. And that's true if you go back in time before I start this data shown here. And the projections have that going forward all the way to the year 2100. We're going to keep using more energy each year. And where this growth is coming from is primarily not us here in places like the United States, but primarily in the developing world. Our growth in energy demand has almost flattened out in places like the United States and Europe, but in places like China, India, Africa, Brazil, These are folks who were using almost no energy on an individual basis, and now they're having refrigerators and air conditioners and cars and computers and cell phones and everything else. And so they're all using more energy going forward. So this growth in energy demand is pretty much unavoidable. So you can look at where we are today. Today we're using about 18 terawatts worldwide. And by the year 2050, that's going to be almost double, 30 terawatts. So keep that number in your head, 30 terawatts. I'm going to come back to that later. Let me ask you guys, though, where do we get most of our energy from today? Fossil fuels. That's where almost all of it comes from. That's coal, oil, natural gas. One more question. Why do we get almost all of our energy from fossil fuels? It's cheap. So energy, when you flip a light switch, you don't care where that electricity came from. You just care how many cents per kilowatt hour you're paying for it. It doesn't matter if it comes from a coal plant or a natural gas plant or a nuclear plant or a solar panel. It's all electricity. And so we're going to take the cheapest option. But what I want to spend a little time convincing you of is that that energy that seems so cheap actually costs you a lot more than you think it does. And there are countless examples of these so-called hidden costs associated with energy. So you know what you pay your electricity provider, and you know what you pay at the gas pump or your natural gas provider, but you're actually paying a lot more money than that for that use of energy. It's just hidden from you. Just a few examples are coal-fired power plants cause thousands and thousands of asthma attacks every year. Those people end up in hospitals to be treated for those asthma attacks. We all pay for that through our health insurance. So it's coming out of our pocket to pay for that, but it's not going to the electricity provider that's using that coal-fired power plant. And there are dozens and dozens of such examples, and there are folks who've tried to quantify this. How big are these hidden costs? So I've put here the cover of two different reports. They're both free. You can get them online. One is from the National Research Council from a few years back, and then there's a more recent one from just last year from the IMF. And what they did is they tried to analyze just how many dollars are we talking about. And their projection for the year 2015, just 1 year, hidden costs associated with energy in that IMF paper was $5.3 trillion. That is a significant fraction of the global GDP. So we're talking about some significant costs here. Now, the biggest of those is this one, global warming. Now, I try not to use this term very often, global warming, and the reason is that when I hear the word warming, I picture something like this. Warming sounds cozy and nice, especially in the middle of the winter. And what we're doing to the planet is not cozy or nice. The term that you hear more often is climate change. Those are actually technically different things, although they're related to each other. But I'm also not a real big fan of this term because change also is often thought of as a good thing. And sometimes in the middle of the winter here, we're kind of wishing for some climate change. The term that I prefer is this one, climate disruption. This isn't my term. It was coined, I believe, by John Holdren, who is President Obama's chief science advisor. And I really like this use of the word disruption because it emphasizes the fact that we're taking something that was pretty much stable and we're knocking it all out of whack. We're not just changing it, we're disrupting it. So what are some examples of where this is manifesting itself in impacts? One is that glaciers are melting all over the planet. This has been very well documented now. And you might not care too much about whether a glacier is going away or not, but glacier meltwater from those glaciers in, for example, the Tibetan Plateau in the Himalayas, that is the source of fresh water for about 1.5 billion people. That's where the Yangtze and Yellow and Indus and Ganges and all those great rivers in Asia, that's where they come from. So when those glaciers are gone, I don't know where those folks are going to get their water from. Sorry, window popped up. I will get us back. Just bear with me. Okay. Another one that you may not have heard about is this one, ocean acidification. So the thing that's causing the planet to warm up and leading to climate disruption is carbon dioxide going into the atmosphere. That's the main culprit, the main greenhouse gas we're putting up there. And a lot of that carbon dioxide stays in the atmosphere, and that's what exaggerates the greenhouse effect, as I'll describe in a few minutes. But a lot of the carbon dioxide gets absorbed in various places, especially the oceans. The oceans soak up massive amounts of carbon dioxide. And when you put carbon dioxide into water, you get carbonic acid. So we're actually making the oceans more acidic with time, and you can measure it. You can measure the pH of the oceans, and it's been going down steadily for many years now because of this phenomenon. And a more acidic ocean has all kinds of bad consequences. One is what's pictured here. I was speaking to a gentleman before the talk who's a scuba diver. He's probably seen this himself. The coral reefs around the planet are dying. They're being what's called bleached, like the one that's pictured there, which doesn't sound so bad. What it means is that it's dead. And that's because those corals can't survive in those more acidic waters. And coral reefs are one of the key bases of the marine food chain and really the food chain on Earth. So that's a scary phenomenon. There are other examples, too, in the oceans where acidic water is a problem. Creatures that form shells, like clams and oysters and mussels and so on, they cannot form their shells as easily in acidic water. Shells essentially dissolve. And so populations of many of those shellfish are plummeting worldwide. Polar melting. So the planet is warming up everywhere, but it's warming most strongly at the poles. And so that's invisible to most of us because we don't go up to the Arctic or down to the Antarctic very often. But this is some scary stuff. So one of the things that's happening is sea ice is melting. When you melt sea ice, which is very bright and reflective, and you end up with open ocean, which is not very reflective, that sunlight that's coming down and heating up the planet gets absorbed more instead of getting reflected back into space from the ice. So you get more warming, which melts more sea ice, which absorbs more energy, and you have a runaway process. There are other examples in the Arctic of this too. The permafrost that populates a lot of the Arctic, inside that permafrost is frozen methane. That's natural gas. And when you thaw it, the methane comes out and goes into the atmosphere. Now, methane is also a greenhouse gas. In fact, it's about 80 times stronger greenhouse gas than carbon dioxide. So climate warms up, melts permafrost, releases methane. That causes more warming, which melts more permafrost, releases more methane, another feedback cycle. There's also something called methane clathrates. This is methane frozen under the Arctic Ocean in the ice. Same thing, as that starts to melt, it's going to come out, another feedback cycle. These are some scary things that lead to what are called tipping points. So people ask, what's going to be in the future with climate disruption, and it is going to be worse in the future, but these things are already happening today. We're having more extreme weather than we've ever had before. There was this serious drought in the Middle East that just ended a few years ago. There was just a paper I saw today that said that that was the worst drought seen in that region in at least 900 years. These kinds of things are going to happen more often. More droughts, stronger hurricanes, and so on. One of those big hurricanes like a Katrina or a Sandy hits a major population center. That's a massive cost for all of us. And of course, there have always been hurricanes, but they're going to get stronger going forward. We're talking about hundreds and hundreds of billions of dollars. So when you have things like droughts or too much precipitation, flooding, and these are the two likely things that we're already seeing happening more often. We get 100-year storms every few years now. Both of those are bad for agriculture. They don't want too much water or too little water. They want just the right amount of water. And so this affects all of us. First of all, food is another big challenge we have going forward to feed a growing population on Earth. But it's going to get harder to grow that food. And that drives up food costs for all of us. There's another one of those hidden costs. So at the grocery store, the supermarket, the restaurant, wherever you're buying your food, those prices are going to keep going up in part because of this. So you don't pay it to the electricity provider, you pay it at the grocery store. So one of the phenomena that is just very inarguable here, so easy to see, associated with climate disruption, is sea level rise. The oceans have been steadily rising so far about 8 inches because of us, and will go much higher going forward. And the reason the sea level rises is actually twofold. One is the one that might seem most intuitive, which is that when you melt land ice from glaciers and other, and it ends up in the oceans, you're adding water to the ocean, so of course the ocean's going to get higher. There's another phenomenon, though, that is actually a significant contributor, which is that the ocean is warming up. So all this heat energy that we're adding to the planet, some of it's staying in the atmosphere, and that's what we feel in our climate, but actually a lot more of it is going into the oceans, and they're getting much, much warmer. And when something gets warmer, it expands. Just like a balloon, if you blow a hot air dryer on a balloon, it'll expand. Same thing is happening with the oceans. They're literally expanding because they're getting warmer, and that is also causing sea level to rise. So again, it's been 8 inches already. It's projected to be measured in feet this century, and if you go into the next century, if we don't make some big changes, it'll get really scary. If you melted all of the land ice on Earth and you put it all in the oceans, they would be over 200 feet higher than they are today. So a lot of these things that I've already mentioned, for example, impacts to agriculture, are leading to global security challenges. So a lot of people don't realize, but one of the main contributing factors that sparked the Arab Spring was a spike in food prices. So when you have shortages of food production, that leads to instability. You have refugees moving across borders. This is a massive global security problem going forward. And the last one I'll mention here, just because I ran out of space on the slide, is health. There are all kinds of connections between climate disruption and health. One that I'll mention here is vector-borne diseases. So the one that's in the news these days is the Zika virus, but there are all kinds of examples of this: malaria, dengue fever, West Nile virus, and so on. These things that are carried by ticks and by mosquitoes are moving to regions on Earth where they never were before because the climate is changing. And so that means these diseases are spreading with them. That is a huge global health cost that's affecting all of us, as you hear in the news every day nowadays. Okay, so just a quick primer on the science so I can tell you how we can get out of this mess. So first of all, what is the greenhouse effect? The sun shines down on us and brings down massive amounts of energy. I'll actually give you some numbers for that energy shortly. And that warms up the surface of the Earth, which then radiates that heat back out towards space. Now, in the atmosphere, we have greenhouse gases like carbon dioxide, but there are some few dozen of these. Carbon dioxide is just the biggest one, that trap some of that heat like a blanket. And that keeps the Earth warmer than it would be if all that energy radiated back out to space. And in fact, that's really important for life on Earth. Because those greenhouse gases are in our atmosphere, it keeps the Earth at a livable temperature for species like us. The average temperature on Earth is roughly 60 degrees Fahrenheit. That is climbing. That's what global warming is. So we need those greenhouse gases. We don't want to get rid of all the greenhouse gases, otherwise we'd all be dead. In fact, if they weren't any greenhouse gases, the average temperature on Earth, if all that energy was radiated back to space, the average temperature would be about 0 degrees Fahrenheit, which is not a very livable planet. So that significant effect from 0 degrees Fahrenheit all the way to 60 degrees Fahrenheit is caused by a tiny amount of gas in our atmosphere. So this pie chart here shows you what the makeup of the atmosphere is on Earth. It is mostly nitrogen. Almost everything up there is nitrogen. Next biggest piece is oxygen. The two of those make up almost the entirety of the atmosphere. And then that tiny little sliver that's left, I blow up in this other pie chart picture here. And you can see most of that is argon. That's just an inert gas. It's not a greenhouse gas. And then there's that tiny little sliver of the tiny little sliver. That's the greenhouse gases, carbon dioxide and some others. So what that tells you is that just a little bit of this stuff in the atmosphere can have a massive effect on our global temperature. And you can see that if you look back historically. So you can go down to a place like Antarctica and drill down into the ice and pull out a core of that ice, an ice core. And it'll look like what's pictured here, where you see layers inside the ice core, and it's like the rings of a tree. Every year, there's some snow that gets compacted down by the snow the next year, and they just pile on top of each other, and you build up layers, with each layer in the ice core representing effectively 1 year, just like a ring in a tree. And what's really cool about these ice cores is that they give you a window into what Earth was like back when that snow fell. There are actual bubbles inside that ice that have air that's been trapped there for all of that time. And so you can sample that air and find out how much carbon dioxide was there in the atmosphere hundreds of thousands of years ago. So the longest of these ice cores goes back almost 1 million years. So we have a really good record of what Earth was like. You can also find out what the temperature was. So here's a data from what's called the Vostok ice core, which is one of the better ones. And there's two pieces of data plotted there in the red and the blue. One is carbon dioxide, and there is temperature. And what you'll notice is they both jump around quite a lot, but they're almost right on top of each other. These two things track each other almost perfectly on Earth. You'll notice another thing when you look at this data, which is that there seems to be a cycle. It spikes up, and then it comes back down, and it spikes up, and it comes back down. And that the period of that, the cycle time, is about 100,000 years. So when you hear about climate change is natural, it's true that some climate change is natural. This kind of thing has been happening on Earth since there's been an Earth. The climate has been changing. But the time scale here we're talking about is tens or hundreds of thousands of years that those time scales happen on, not on the time scale of decades. One thing I want to point out to you is look at the y-axis scale there. So in the blue there, that's the concentration of carbon dioxide that's in the air. And again, it goes up and down over that time scale of tens or hundreds of thousands of years, but the maximum on that scale is 300 parts per million. It never went above 300 parts per million. Here you can see about 350,000 years. You can actually go back 800,000 years, and you still will never go above 300 parts per million. Remember that. Because then, oh, one more thing. Let me explain why it does that, which is that we're getting this radiant energy from the sun, and it's going back out, but the Earth's orbit around the sun changes very slowly over time, and the way that it wobbles and the angle at which it points, all these things change just subtly over very long periods of time. There's a scientist a long time ago who figured this out, called Milankovitch, so they're called the Milankovitch cycles, and that's what leads to that 100,000 year up and down are subtle changes in Earth's orbit. That has nothing to do with us. That's what's been always going on. But then we came around, and we started building these things. That's a coal-fired power plant. And we started putting carbon dioxide into the atmosphere. So if anyone who tells you that we're not putting carbon dioxide into the atmosphere, here's the data. This is data taken from Hawaii, measuring the atmospheric carbon dioxide concentration, and you can see it climbing up every year. The little wiggles are because of seasonal variations in vegetation, where plants grow in the summer, they absorb some carbon dioxide, and then they die off in the winter and release it back. So that's what the wiggles are. Obviously, this just keeps going up. Now look at the numbers. Remember I told you in 800,000 years, in fact, in about 3 million years, it's never gone above about 300 parts per million. Look where we are. We're almost at 400. That's basically where we are today, is 400 parts per million. So right now we have an atmospheric chemistry that is unlike anything that has been on Earth since long before humans were ever here. What that means is that we're going to end up with a climate that is unlike what humans have ever seen. And in fact, you can see that the temperature is rising. Again, inarguable data. This is air surface temperature. Remember, a lot of the heat is going in the oceans, but some of it stays in the air, and that's what we feel. And here's your temperature rise becoming most striking starting in the 60s and 70s and going forward. So we've already gone up almost a degree and in Celsius, and the sort of consensus for what the scary number is about 2 degrees, and we're on track to go well past that. That's what the climate accords are all about, is trying to keep that from happening. So what can we do? That's what this talk was promised as, that it's not all doom and gloom. So we basically have 3 types of options: mitigation, adaptation, and what I think the scariest option is geoengineering. So none of these options are great, but this is what we've got. I like this picture. On the road to success, there are no shortcuts. So it's going to be hard, but this is what we face. So adaptation is something we're going to have to do no matter what, because as I said, climate disruption is already happening, and no matter what we do starting today, there's still going to be more changes, more disruption, so we have to prepare and adapt. That involves all kinds of things: planning for resiliency, so that when a major hurricane comes in, we're more prepared to respond to it, maybe moving people from regions that just are no longer sustainable to other regions. Sea level rise is already a massive problem in cities like Miami and elsewhere. Low-lying cities all around the world, all through Southeast Asia and Tokyo and elsewhere, will eventually be more or less underwater. New York City is another one. In some cases, you can build seawalls. In other cases, you can't. In Miami, that's not going to help you because it's built on porous rock and the water will just go right under your seawall. So we're going to have to do some of this adaptation no matter what, but you can't adapt yourself out of climate disruption. Now, to give you a sense for how scary the situation is, serious people are talking about doing this, geoengineering, which is using the entire Earth as a laboratory, as an experiment. Now, we've done that inadvertently already by putting all this carbon dioxide into the atmosphere and changed the chemistry, and that's what's causing the climate to be disrupted. So we've already done this. But now the question is, well, maybe we can engineer it back by, for example, putting aerosols into the atmosphere that'll reflect more sunlight back into space and keep us from warming up so much. And some of these, maybe they would lower the temperatures if you really did them on a truly massive scale, but I guarantee you all of them would have all kinds of unintended consequences, which could very well be worse than the problem you're fixing in the first place. So I sure hope this is not what we have to turn to. So what's left? Mitigation. And how do you mitigate climate disruption? You start putting less carbon dioxide into the atmosphere, and you start doing that soon and in a big way. So where can we get our energy from? So I've shown here a series of boxes that I've scaled in size to represent how much energy we can ever get worldwide from these different sources if you got it everywhere you could feasibly. And don't take the numbers as exact. They're plus or minus some amount. Of course, there's some uncertainty here. So you'll notice fossil fuels could power the entire planet. They're doing that today, basically, and they could power the entire planet in the future for a long time. You could get 30 terawatts, which is where we're going to be in 2050 from fossil fuels. So yeah, oil will run out at some point, but there's enough coal to last for maybe 1,000 years. So we're not going to run out of these things anytime soon. I hope that's not the solution we turn to. Nuclear energy could be scaled up to power the entire planet, but to get to that type of scale, a 30 terawatt scale, you would have to build a new nuclear power plant every day, starting today, all the way to the year 2050. So that would be a massive, massive expansion of nuclear. I'm not sure we can afford to do anything near that scale. And of course, there are all the related issues of what to do with the waste and proliferation concerns and so on. It'll need to be a piece of the story, but I don't think it's the one and only answer here. And then we have the renewable energy sources. And you'll notice they're not all the same size. Not all energy sources were created equal. So one I tend to pick on, not because it's a bad energy source, it's just not a big one, is geothermal. So the main way you get geothermal energy is you drill through the Earth's crust and you get to that heat that's down there. And you use that heat to boil water, to make steam, to turn turbines, to make electricity. Just the same way a coal-fired power plant works, except you're using the Earth's heat instead of burning coal. And it works great in the places where you can actually get through the Earth's crust. But there's only a few places where the Earth's crust is really thin. So Iceland, for example, gets lots of energy from geothermal, but worldwide it's never going to be a big contributor. It doesn't mean you don't do it, it just means it's not going to solve our problem by itself. So I told you earlier that globally today we use 18 terawatts of energy. That's an 18 terawatt box. And I asked you at the beginning, where do we get our energy from today? And you said fossil fuels. There's the numbers. The light gray part of that box is the fossil fuels, and you can see it's almost the entire box. Next comes nuclear and hydropower, and then pretty much insignificant contributions from all those other sources. But that's where we are today. I'm not so concerned about today. Well, I'm concerned about it, but I can't do anything about it. The question is, what about in the year 2050? I have a 13-year-old. What about when he's middle-aged in the year 2050? What's our energy mix going to look like? And so remember, we're going to need almost twice as much energy then. It's going to be 30 terawatts. And so you can ask the question, how are we going to put these different energy sources together and get ourselves to 30 terawatts? And there are folks who've tried to project that, of course, and said, what is this likely energy mix going to be? And obviously there's differences of opinion in that. But a rough picture of what people are saying is something like this. So all those other energy sources grew dramatically, some of them multiple-fold. But so did the fossil fuel use because we needed so much more energy. So this is an unacceptable scenario. This is not using less fossil fuel and decreasing our emissions. This is actually increasing emissions. So this better not be what our energy mix is in the year 2050. So let's just play a hypothetical game and say we're not going to use any fossil fuels in 2050. And I'll go on the record now and say I think that's unlikely. We'll probably be using some fossil fuels even in 2050, but just hypothetically, what if we didn't want to? And let's just say we wanted to avoid nuclear, to avoid challenges with the waste and so on. How much could you get from these renewable energy sources? So what I'm going to do is empty out all those boxes, all the wind and biomass and hydropower and so on, everywhere on Earth that it's really feasible to get. How much energy could you possibly get? And you end up with something that looks like this. You can see we're coming up short. But if you were paying attention, you'll notice there's one energy source, one box that I didn't show you yet, and that's solar energy. So how big is that box? So I'm actually going to go to circles instead of boxes. So that's a circle. It's just too big to fit on the screen. And that's the amount of energy that's hitting the surface of the Earth from the sun all the time. And it is a massive amount of energy. It's actually enough energy hitting the surface of the Earth in 1 hour to power the entire planet for a year, which sounds really impressive. Except, of course, you can't capture all of the energy hitting the surface of the Earth. So the question is, what's feasible? What could you actually get? So I'm just going to do a back-of-the-envelope estimate just to give you a ballpark for how big this resource is. The first thing I'm going to do is I'm going to throw out the oceans. We're not going to put solar panels all over the oceans. So that gets us to a smaller circle. Now, you also can't, of course, cover all the land area with solar panels. You need all kinds of other things on land, like farms, for example. So let's say, what's a reasonable amount of land to cover? How about 2%? So 2% is roughly the amount of land in the United States covered by roads. So that's a lot of land. It would look something like that. I'm not saying we'll put them all in west central Kansas, but That's 2% of the United States. It is a good location for solar panels, actually, but we won't put them all there. So this is feasible. It would be a big deal to build that many, but it's possible. So now we're down to an even smaller circle, but there's another problem. You can't convert sunlight to electricity with 100% efficiency. There are fundamental losses in that process. So the best you can do, according to the laws of thermodynamics, is about 30%. And you can buy a commercial solar panel for your rooftop today that does it at about 20%. So actually, solar panels work really well. They're approaching the limits of what's even possible with a solar panel. I'm going to be more conservative than that. I'm going to say 12%. So that's a very feasible number for average conversion efficiency. So now we're left with a circle that's a pretty embarrassingly small fraction of that monster that we started with, right? But that tiny little measly circle there on the side of the screen is that yellow box. So the feasible solar energy supply is more than 2 times larger than the total projected global energy demand all the way out in the year 2050. In fact, it's larger than the projected demand in the year 2100. This is, for all intents and purposes, an inexhaustible energy supply. And it's not surprising that the solar energy supply is larger than wind or hydropower or biomass, the next 3 big guys there, because those are solar energy just going through extra steps. The reason the wind blows is because the sun heats up the air and you get convection and so on, and that causes some wind to blow, some of which you can capture with turbines. So it's going through extra steps. Obviously, the supply is not going to be as big. Biomass, that's plants using sunlight, doing photosynthesis and making chemical fuel and other things. Extra steps, it's not going to be as efficient. Hydropower. How do those dams work? Well, the sun evaporates water. It goes up into the atmosphere. It comes down as rain or snow, and that comes down from the mountains, and you dam that up in the rivers, and you get hydropower. So it's solar power evaporating the water in the first place. Again, extra steps. Now, I don't show this picture to suggest we should get all of our energy from solar energy. That is not the case. We want an energy mix for all kinds of reasons. But the point is that solar has to be a huge piece of the story going forward. We have no choice, in fact, because we need to turn to mostly renewable energy, and it's the only one that can give us as much as we need. So yes, let's do wind and hydropower and geothermal and all the others everywhere you can, but solar's got to grow like crazy. So how do we get there? So one thing I didn't mention yet is efficiency. So the cheapest energy source that you can have is energy efficiency, using less energy. And that is absolutely the first thing we do. We should all have better insulated homes and low flow faucets and drive high MPG cars and all of that, more public transit and so on. All those ways we can be more energy efficient, we have to do all of them. But that does not solve the problem. It only gets you a little piece of the way there. So we do that first because it's the cheapest way. But then we just got to start shifting the way we make energy on a huge scale. And there are various ways you can make this happen. One is with a carbon tax. So I told you there's all these hidden costs associated with the use of our energy, one of which is climate disruption, but there are countless others. We're paying for that already. Again, this isn't some new expense for us. We're already paying it on our health insurance and tax dollars and all over the place. You can put that cost in front of the consumer and let the market take care of the problem for you. You take an external cost and you make it visible, then the market will start using what are truly less expensive sources, which are the renewable sources. Another way to get to that is a cap and trade system, also letting the market take care of it. And that's effectively what those Paris Accords were all about, this big agreement that just happened at the end of last year in Paris, where all the countries agreeing to put caps on their emission at certain levels. That's another approach. So there's another important piece to this story, though, which is research and development. So I'm advocating for solar to be a huge piece of the energy mix going forward. And the technology that's available today, the primary technology for that are silicon solar panels, which are awesome things. They're really efficient. The 20% efficient solar panels I mentioned, those are silicon. There's lots of silicon on Earth, so we can make as many of these as we want. But there is a challenge with them. One, they're a little bit expensive, although costs have been coming down a lot. But there's a bigger challenge with them, which is that you have to invest a lot of energy to make them. You need super pure silicon, and it's got to be crystalline to get a high-efficiency solar panel. Both of those things take energy. So you invest energy in, and then it takes a while to get that energy back out once you plug it in. And in fact, it takes a few years. And there's nothing we can do about that with silicon. So if we really want to scale up solar power super fast, which is what we have to do, I mean, the market's already growing at something like, I don't know, 30% or more per year, which sounds like massive growth, but that's nowhere near enough. It's got to grow way faster than that to solve this problem in the time frame dictated by climate disruption. So we need new technologies, and one that I can mention that we study at Argonne is this one here. This is a organic solar module, and that's not organic like produce at Whole Foods. It's organic meaning it's based on carbon-based molecules. So that reddish purpley color you see there is a blend of a polymer and a small molecule called a fullerene, interestingly enough discovered by Rick Smalley, that's what he won the Nobel Prize for, blended together. And you can put those two things into a solution and make an ink, like the ink in your pen, and you can print or coat your solar panels in a roll-to-roll process where you have a roll of plastic on one side, it goes through, gets coated just like newspapers, laminated, and you got yourself a working solar panel. I can charge up a cell phone with this guy. So this is just one example of one of the technologies that's on the horizon that has much less energy embedded within it, and so we can scale it up much, much faster. To really get those technologies ready for the market, though, we're going to need some more research and development. So before I open it up for questions, I just want to show this picture. So that is a picture of Earth, obviously, taken from space, and the sun was just coming up around the horizon there. And that little blue line you see around the planet, that's our atmosphere. So when you look up in the sky, it looks huge, right? It seems to go on forever. The atmosphere is so much bigger than us, it seems like it's almost infinite. But in fact, it's a razor-thin blanket going around the planet, protecting us from that really awful environment out there in outer space. And we are messing with that razor-thin blanket by putting all this carbon dioxide up there. We need to start changing that soon. So thank you, and I would be happy to answer any questions you have. You can wait for a microphone 1 second, just so I think that way the folks who might be watching online can hear. It's back here. The gentleman with the beard there. Oh, sorry. Well, if you can just yell out your question, I'll repeat it while they're getting the mic working.
I'd like to get your comment on two scenarios which I think provide concrete evidence that our efforts are doomed to failure. Number one, the recent decision by the U.S. Supreme Court annulling the EPA plan to regulate greenhouse gas emissions. Number two, something that happened in Chicago Section American Chemical Society meeting 2 years ago. The former chairman of the board and president of the ACS lauded hydraulic fracking and mentioned there will be a $6.8 billion construction in Appalachia of a petrochemical plant to process fracked natural gas. I took him to task and he gave me a tongue lashing, but it seems to me that those two scenarios show that we're hopelessly mirrored in the fossil fuel paradigm, and when we wake up, it will be far too late. We will have exceeded the climate tipping points.
Okay, so thanks for those points. Yes, it is scary. I oscillate myself back and forth between kind of giving up hope and having hope. So to address the 2 points you made, for those who don't know about the Supreme Court decision recently, the EPA enacted or tried to regulate something, they called it the Clean Power Plan, which was going to, it basically classifies carbon dioxide as a pollutant, which the Supreme Court did say is okay previously. And then they were going to basically limit emissions that way, and that would effectively end up shutting down a lot of coal-fired power plants. About half or so of the states in the country sued the federal government, having various complaints about this plan, and it made it up through the courts. The Supreme Court issued a stay. So they didn't overrule the Clean Power Plan. They issued a stay, meaning you can't start enforcing it now. So it's going to go back to the lower courts and so on. And I'm not a legal expert, so I don't know the whole process. But it's not a dead plan by any means. But it is frustrating, absolutely. One of the challenges with climate disruption is that it's become a political issue when there's no reason for it to be a political issue. It's science, right? The science tells you this is happening, that we are the cause, and somehow it's turned into this great political debate where If you're from a certain type of, from one party, you're not even supposed to believe in climate disruption. But whether you believe in it or not, it's happening. And what I like to emphasize is that it doesn't matter what party you vote for or what religion you are, if you have no religion at all. We have all kinds of disagreements, but something that we all agree on is that we want our children's lives to be better than ours. And that is a future that we're putting at risk by disrupting our climate. And that is how I think we can appeal to all of our fellow humans to try and solve this problem. Now, the other point you brought up was hydraulic fracturing. So hydraulic fracturing has been a great boon for the US energy independence and for the US economy. So we are now, I believe, a net energy exporter, which people never would have thought was possible not too long ago. So hydraulic fracturing is where you inject these fluids down into things like shale deposits, and it cracks the shale, and that releases natural gas and oil and other things that have been down there, and it all comes up and you can use it. So that makes our energy prices much lower here, which is good. Now the challenge with this is that, first of all, natural gas is methane. I told you earlier that's a greenhouse gas, 80 times stronger than carbon dioxide. Now, you're not releasing the methane in principle, but there's leaks everywhere when you do a process like this. There's pipelines and processing and so on, and those things leak methane. So we're actually putting a lot of methane unintentionally now up into the atmosphere, so natural gas is cleaner from a carbon perspective than coal is, but if you're putting up lots of methane, it's not actually an improvement. So we need to limit that as much as possible. The other issue is that, so yes, natural gas releases less carbon dioxide than coal per unit of energy that comes out of your power plant, but the average carbon intensity of our energy mix has to be lower than that of natural gas in order to mitigate the problems of climate disruption, and natural gas is the fossil fuel with the lowest carbon intensity. What that means is it doesn't solve the problem. It moves us a little bit in the right direction, but we got to get off all of the fossil fuels. You're right. That was a long-winded answer, but sorry. Sure, right here in front.
Two parts coming from two observations with the presentation. First part is there's an old joke about technology is the stuff we invent so that we don't have to experience real life directly. And whenever I come to climate discussions, it's always about more technology, more technology, more technology is going to solve the problem. So the first part of the question is, and I never hear this in any climate disruption presentation I ever hear unless it's one of mine, what do we need the energy for? Nobody asks the question seriously, so we never go about answering it. I mean, if it's to make more Barbie boutiques for our kids or wall-to-wall televisions in our home, should we even survive as a species? But the second part of that is, if we're not going to use technology, then we have to look at limiting per capita energy intensity, which is a real social science problem. Because even if you have good technology, it gets undone by unforeseen social science effects. Energy efficiency is a good example. CFCs were going to save all this energy, so I'll just leave the light on from now on. Totally defeats the purpose. Or instant-on technology wiping out all of the efficiency gains that were gained over a decade. So where's the role of social sciences, and where are we ever going to get serious about reducing per capita energy intensity instead of inventing our way out of things with stuff like fusion?
Yeah, so those are a lot of great points, and you're absolutely right that science and technology are just one of the tools in our toolbox to address this problem. So you mentioned social science, that's another big piece of it. Education is another big piece of it, and another big piece is policy. Policy and law and all those other aspects that's what puts all of these things like a carbon tax and a cap and trade and so on, which drives the market to make the right technological decisions. So almost all aspects of our society have to attack this problem. It is going to end our civilization if we do not. Now, you talk about energy use. We are very selfish here in the United States. We use more energy per capita than just about anybody else, and we have for a long time, and so we've been the main causes of a lot of this problem. And now developing countries like China are becoming larger emitters than us, and we're yelling at them, you can't emit all that carbon dioxide. We don't stand on very firm ground because, of course, we were the primary emitters up until relatively recently. And per capita, we're still emitting a lot more than they are. So yes, that would be great if we all were willing to, ride in carpools and, not have appliances in our house and all these other things that we've become used to in modern society. But I just don't think that's a realistic outcome from where we are today. I don't think we can convince everyone to change their lives back to when the per capita energy intensity was so much lower. But what we do have an opportunity to do is in this developing world where you have China and India and all this billions and billions of people who their per capita energy use is so low, they're going to be using more energy, and you can't tell them not to use that energy. It's their right to use it just as much as it's our right to use it, right? And a lot of that energy is doing things like saving lives and improving quality of life, so that's important that they use that energy. A light bulb in Africa can let a student read and do their homework at night and become educated and make a bigger impact on Earth because of that. So you can't take that away from people, but we want that energy to be coming. We have this opportunity. They don't have the infrastructure built in place for fossil fuels that we have. We have this opportunity to get that energy from renewable sources, and that's what we need to do. Yeah.
Thank you. That was very interesting. So I think what I have to say is that we have to blame this on you and your colleagues. What are scientists and educators doing to make the public and their politicians pay attention? I mean, why don't you get together and say we have to devote 20% of our time going out and getting on TV, writing, protesting, talking to our students, going tell them to talk to their parents. You guys are the one who can explain it. Why aren't you doing so? And collectively, what are you going to do about it?
Yeah, so you're right that there is a responsibility on the scientific community to communicate the science to everyone else so that they understand the scope of the problem and what can be done about it and so on. So some of us do this, right? I'm standing here talking to all of you and anybody online trying to get this message across. Now, why don't we all spend 20% of our time on it? There's an easy answer to that. My salary is paid by you guys. I work at a national laboratory that is owned by the Department of Energy. The funding that funds our research comes from tax dollars, and we are funded to do research, not to go out and talk to all of you. I'm here after hours doing this talk, right? So if you as a taxpayer and voter would like to see more people in the scientific community doing more outreach and education, communicate that to your representatives and get that through the system and give us the permission, if you will, to go do that. Give us the resources to be able to spend our time doing that rather than all volunteering, because we really do think this is important, like I'm doing now. There's a bunch back here. Just I don't know where the mics are.
Mine is sort of a follow-up on his question. I mean, we have 3 energy bills pending in Illinois. One of them is an Exelon bill, which is going to try to drive tons of money toward more nuclear, propping up the old infrastructures of old plants. Another one is ComEd. Short version, I guess, is that the ComEd bill is going to continue with the fossil fuels and going to try to control the rate at which we build into renewables. The third one is the Clean Jobs Energy Bill, and it's been written probably by the lawyers at ELPC and RDC, and it actually would fix the renewable portfolio, as we understand it. And it's not a perfect bill, but it's a very, very much better bill in terms of moving Illinois into 21st century energy policy. So couldn't the scientists in Illinois help us a little bit? We've been working on this for a year and a half. We don't know when Madigan and Cullerton and Ronner are going to actually push those bills into a final bill, but as Dave Kraft would say up here, these are not bills that you should make sausage out of, and especially given the data that you've just given us tonight. But we need help to get, the Tribune won't take an article from me, but they might take an article from you.
Yeah, well, the Tribune has taken an article. I've got an op-ed that was in the Tribune.
But we have to
exactly
get the
that.
media saturation, right?
Yeah, well, I mean, I guess there's only so many of us. But so I'm going to stay a mile away from talking about Illinois politics, because I'd get myself in trouble really fast if I started talking about that. So back to the Clean Power Plan. The way that the Clean Power Plan is designed is that each state is told effectively, here's how much carbon you can emit, and then that's taken into account. When you put all the states together, that keeps the nation within what we've promised in the Paris Accord. And then it's up to the state to decide how to reach that. And they can do it any number of different ways. They can buy renewable energy credits, they can shut down plants, they can build solar farms, whatever it is they think is best for their state is their freedom to do. So each state is supposed to prepare a plan and submit it to the EPA and work that out. And some states have done that and some have not. Illinois has not done that yet. So I think that is a good avenue to solve this problem, is rather than reinventing the wheel with regulation from the bottom up within the state, adopting something like the Clean Power Plan, having an Illinois state plan that is enmeshed with that will meet the targets of that plan. I should point out, though, as exciting as it is that the world finally came together, more so than Kyoto back in the 90s, that the world finally came together in Paris and agreed to reduce emissions pretty dramatically, much bigger promises than we've ever had before. That's a sign of optimism. But you have to realize that even if all of those targets are met, which is an if, that is not enough. We need to get even further to solve this problem. How about here in front? Oh, sorry. Yeah, go ahead. You're there. Go ahead. I'll get to him next. Anybody?
Thank you. I was surprised to hear you say that geothermal would never be viable. Is there a physical limitation on?
So I want to be very clear. I did not say geothermal is not viable. It works great. Iceland gets most of their energy that way, I think.
Right.
So it's a wonderful energy source. It's just not a huge one. So there's only so many places where it's feasible to drill down through the Earth's crust, because most places it's way too thick and we just don't have a technology that can drill through that many miles of crust to get down to the heat. So it's the areas that are volcanic, basically, because that's where the Earth's crust is thin. You can get through and get some geothermal energy, and absolutely, let's do it. It works great. But even if we did it everywhere, it's less than a terawatt of energy worldwide. So yes, we do it, but it doesn't make a big dent in the end. Yeah, unless, well, sure, maybe somebody can invent a way to drill down, much deeper through the crust than we've ever done before. I'm not sure that technology is going to come out on a time scale that is put on us by climate disruption. We would need that technology to come out basically today so that you could roll it out over the next few decades and actually put it in place. Maybe that's possible, and if someone's working on it, that's great, but I'm not aware of that being a feasible scenario. Okay, over here, yeah, sorry.
Thank you. I'm super excited about a lot of the questions. I hope it's okay. I actually don't have necessarily a question as much as an encouragement. I am working on the Clean Jobs Bill. We are in negotiations right now with ComEd and Exelon, but we need you. So when you say, sir, that that the fossil fuel industry is working hard to stop us, yes, they are, because they have financial investments involved right now. We're in a very awkward time in history of transition, and transition takes courage. And we need voices. And so in order to have change happen, we need to demand change and keep pushing hard for it. So the Clean Jobs Coalition is working very, very hard to fight those forces. While we're in transition, we're not going to get everything that we want. But please, I encourage you to stay involved, to stay optimistic. This is not a short fight. This is not going to be the first piece of legislation that happens in Illinois, nor will it be the last, but it is a step forward. And once we take that step forward, then we can start running. I am the vice president of the Illinois Solar Energy Association, and I'm so excited to see these numbers because I do get very depressed about climate disruption. I love that term. I'm going to adopt it, but we have to remain hopeful. We will never see the fruits of our effort. The changes that we're talking on the scale that we're talking probably won't happen in our lifetimes, but we have to plant those seeds. The responsibility is ours right now, and we have to act hard and we have to act together.
And let me just add one more point to that, which is I give a lot of talks in schools, especially high schools, and it makes me very optimistic when I talk to those kids because I give talks in some very red districts, and I'm sure a lot of those kids' parents are not particularly supportive of renewable energy plans, but the kids are, for the most part. They get it, and they're the ones who are inheriting this problem. So I think they know that it's got to be fixed, and that's the generation that's going to be affected, and it's the generation that's going to ultimately fix it. How about way in the back?
Thank you. My question is about looking at this problem as perhaps a bit wider than you were talking about, more to your initial slide about the variety of different issues, but thinking about this as can we solve a much bigger problem, or is it necessary to solve a much bigger problem in order to solve the climate disruption problem? And I'm talking about poverty and income inequality and all these things, because trying to imagine what a sustainable world would look like in the future sometime, but one in which all these major issues still exist, I'm doubtful that we can potentially get there if we don't solve these other problems.
Yeah.
And potentially missing an opportunity to solve them all at the same time. Maybe that's too ambitious, but
No, you're
perhaps
right.
the scale of what we're trying to do is extremely ambitious anyways, and the only potential opportunity to get there is to do all of them at the same time.
Yes, you're absolutely right. And in fact, there's even a name for it. So if you looked at the top 4 things on my list, or Rick Smalley's list, were energy, water, food, and environment. And there is something called the energy, water, food, climate, or environment nexus. And it hits on exactly your point that all of those things are interrelated with each other. So I spend a lot of time telling you how energy and climate are related, but energy and water are related. The biggest withdrawer of water in the United States, power plants. Something like 200 billion gallons a day go through power plants. So water and energy are related that way. One of the biggest uses of our electricity is the cleaning and distribution and heating in your homes and so on of water. So energy and water are intimately related in all kinds of different ways. Same goes with food. To grow food, you need water. So we can help solve the water problem. That addresses the food problem. If you can make crops that need less water, that helps you, and so on. I had another point I was going to make, and I forgot it. But yes, all of those points are interrelated with each other, and absolutely, progress you make on any one of them is going to help you with all of them. Considering them together is the right approach. Right here, Mike.
I remember you had a slide about geoengineered solutions. Are there any I should be scared about?
All of them. All of them. Well, okay, so one of them was planting forests, I think, on my list. That's not too scary. Planting forests, we can absolutely do that. But most of those ideas are pretty scary. So when there's a volcano eruption, a big volcano eruption, it puts a lot of aerosols into the atmosphere, and you can actually see a cooling of the Earth when that happens because of those aerosols that were blasted up into the atmosphere. It's measurable. So Pinatubo and all these huge eruptions, if you go back through the climate record, you can actually see the temperature drops because of those. Of course, they're transient because all those aerosols eventually settle out, and then it just goes back to where it was before. So people are talking about seeding the atmosphere with massive, massive amounts of aerosols on purpose to do exactly that same effect. And it would reflect more sunlight back into space, which would make us warm less, but it's going to cause all kinds of other problems. I mean, if you use sulfates, that's going to make acid rain, which would destroy crops and infrastructure and everything. I just sure hope we don't have to turn to those geoengineering approaches.
Thank you for the presentation. I had a question. You mentioned that about the emissions and how China's going up and U.S. has a lot of consumption itself on energy. Well, here in the U.S., there's a lot of potential for offshore wind. Mm-hmm. And why isn't the government investing in that?
Okay, so...
and including right here in Chicago.
Yeah, so I'm gonna avoid stepping into political realm, but to answer your question technologically, offshore wind is a great resource. There's a lot of wind out there, and you're not getting in anybody's way usually when you're offshore. Anyone who stood on a shore in Maine or something, or in Massachusetts, it's pretty windy out there. So yeah, we're going to need a lot of wind energy. It's got to be a big piece of the story going forward. Onshore wind, if you ever drove down I-65 down towards Indianapolis, you've seen one of these massive wind farms. There's some here in Illinois too, and all over the Midwest. So onshore wind is great. Offshore wind is great. We got to do all of it. Why are we not doing more of it? That's a big, complex question, and we're the ones who all have to change that. What can we do to encourage that? You can vote. You can educate people. You can talk to all your friends. You can go lobby people in Congress. All the above. So I'm not familiar with the local politics enough to so the question was, what are the barriers here locally in Chicago to something like, I presume you're talking about Lake Michigan wind farms. I know there's been a debate up in Evanston on the North Shore about this for some time. Colleagues of mine who live up there have been, I think, pushing to get those wind farms built. I don't know enough details to comment intelligently on it. You're right that that's all I can say. Yeah. So for those who couldn't hear, what he was saying is that there was a wind turbine off the museum campus here, I guess, and it was taken down because of ordinances. And then again, what I mentioned about Evanston, that there's been a debate up there about the offshore wind for a while now. Yes, some people consider it an eyesore, and you're going to fight these battles. Solar panels come up against these things too. Sometimes even against environmentalists against each other. You want to put a solar farm out in the desert in California, you might take out habitat that is inhabited by the desert tortoise, which is an endangered species. And so obviously, there are going to be environmental groups that say, wait, don't do that. But if you don't build those solar farms, then we're getting that energy from coal or some other thing, which is, of course, much worse for the entire ecosystem. It's a complex issue. You're going to run into obstacles all over the place. You just got to keep pushing forward. Let's get a question from someone who hasn't asked one yet. On your other side there, sir.
Thank you. Could you give us say a few more words about the organic technology that you're developing?
Sure.
Efficiency and
yeah, sure.
cost.
So, and to be clear, by the way, we're not the only ones studying organic solar cells or other next-generation photovoltaic technologies, solar cell technologies. There are pretty much every major research institution in the world, including here in Chicago, University of Chicago, Northwestern, UIC, others, all have active, groups studying these next-generation photovoltaics. So this particular technology, organic solar cells, the record right now for the efficiency of a cell is around roughly 10%, a little better than 10%, which is not bad. That module right there is not so hot. That's probably a 1 or 2% power conversion efficiency module. And that's one of the things we want to understand is why you have substantial losses when you go from a little cell that you make in the lab to a big module like that. Another challenge with them is their lifetime. So if you put those out, so this one I've had for years, and it works just as well as the day I got it, but that's because I keep it in my office. If I put it outside, and I've done this with other ones, they'll die here in Chicago, especially in the winter. And the reason is that in the temperature changes, especially freeze-thaw cycles and precipitation, you end up with moisture ingress into that, through that plastic and down into the organic materials, which degrades them, and it basically stops working. And so that's another area of active research, is studying ways to get better barrier coatings that keep that from happening and try and extend the lifetime to make them more technologically feasible. And there are lots of other next generation technologies too. This is just one. Another really exciting one if you want to Google it, is perovskite photovoltaics, which have taken the solar world by storm in the last few years. They have efficiencies that rival silicon already, and that just came up from almost nothing a few years ago. So folks are really excited about that one. You spell it P-E-R, geez, put me on the spot, P-E-R-O-V-S-K-I-T-E. They're named after Lev Perovsky, a Russian mineralogist who discovered the mineral called perovskite, which is the same structure that they have. Over here.
Could I ask a question? I've always been curious. You mentioned that you're a proponent of solar. To what extent would solar have to become prevalent? Like if half of all residential houses went to solar and got off the grid, what kind of dent would that actually make?
That would be a huge dent. So yeah, you can almost do it with rooftops in the United States if you covered them all. I'm not sure that that's necessarily the best route, but it does hit on, by the way, another point which I didn't make. Well, let me make a positive and the negative point. The positive one is that solar is a way that we can get away from this model of centralized energy generation that has been developed over a long time in this country, where you have power plants that make energy and spread it out, to a more democratized form of energy where you make your own on your home or your business. And so it kind of wrests some of that control of that energy from someone else and brings it back to you, which I just think is a positive development. But it also has positive developments in terms of the stability of the grid itself, where if a power plant goes down, you have tens of thousands or hundreds of thousands of people without power, whereas when you have distributed generation, you can avoid that problem if the grid is smart enough to accommodate it. So that's a positive aspect. Something I didn't mention, which is very important to mention with solar and wind, is that they are variable energy sources. The sun does not shine all the time. Well, it shines all the time, but it doesn't shine on you all the time. And the wind does not blow all the time where you are. And so sometimes your solar panels, especially at night, or your wind turbines are not going to be making energy. And right now, that variability in supply is not a big problem because it's a really small piece of the total on the grid. But when it becomes a really big piece, that is going to be something that we have to worry about. And so you need another technology to solve that problem, which is energy storage. You need a way to hold on to that energy when you're making extra and then take it off later. And that could be done with batteries and thermal storage and all kinds of different technologies. And those are all also active research areas. Back there, behind you, Chris. Oh, sorry, I'll come over there next.
Thank you.
Sorry.
Oh.
Who's going first?
My question is going on with the previous one, so maybe I can just ask this question. It was about the fact that you said that this equipment, this solar panel, the energy storage equipment, they have a lifetime. So could you maybe put in perspective the fact that we have to produce this equipment, and if we have to reach this stage of all this solar power that we need, how much resources that we need to produce them, and how this can be renewable? Because if we have the energy as renewable, what about the equipment that produces renewable energy?
Good question. So the proper way to evaluate that is to do something called a life cycle assessment. That's where you look at your process all the way from cradle to grave. So you look at the extraction of the raw materials, the silicon in your solar panel, which comes from quartz sand, the aluminum that makes the racking for that panel, all the different materials, the glass, all the pieces that go into a solar panel. You start all the way from the raw materials, mining those from Earth, purifying them or processing them or however what you have to do, assembling them into the panel, encapsulation, all of that, transporting it to where it's going to go, and then also recycling it or disposing of it at the end of its life. That's the whole life cycle. And there are people who are professionals, including colleagues of mine, at doing that quantitatively, and they're very good at it. And so that's the right way to answer those types of questions about sustainability. So in terms of the lifetime, the commercial solar panels, like silicon solar panels, usually come with a guarantee from the manufacturer of 25 or 30 years. And in most cases, they'll actually last a lot longer than that, maybe 50 or more years. So you're unlikely, if you put them on your rooftop, to have to replace them yourself. It would be the next homeowner that would probably have to deal with that problem. And remember, the climate challenge that we're facing is something in the next few decades. So yes, we have to deal with recycling and disposal of those materials at the end of their life, but that's a minuscule concern compared to the scale of the climate disruption problem that we're facing. But an important point is that a lot of these new technologies, these thin film technologies, are just a lot less material. You saw the thing is mechanically flexible and lightweight. It doesn't need mechanical racking and all that other kind of stuff. It also means it's cheaper to install because you don't need professional roofers and all of that to put it on your rooftop. You can just buy a roll of it, at Home Depot someday and roll it out on your roof. So there are all kinds of ways that these next generation technologies have advantages over technologies like silicon. Okay, there were some over here. Yeah.
Is this on? Oh. Hi. Terrific talk. I'm really enjoying this. You mentioned before this goes back to a previous question. Some of us were very excited and looking forward to the COP21 talk or the COP21 conference, and I just was wondering to what extent would this have solved the problems or didn't solve the problems? Maybe, and also President Obama went to the COP21 with a clean power plan. To what extent is his clean power plan lax or gets to where we need to go? And I know you mentioned that before. And maybe you could also distinguish. There are two things in Illinois. One is the Clean Jobs Bill, which is legislative, but we're also trying to implement the Clean Power Plan in Illinois. But that's already EPA. That's already law. Maybe just distinguish that. I think there's some confusion.
Yeah. Okay, so how far does it get us? That's a hard question to answer because the question is, what is the target? Where do we want to be? And I guess the snarky answer to that is, where we were, in the early part of the 20th century. We're not going to get back there, right? We've already made a mess for ourselves that we can't completely clean up. So the question is it going to be bad or is it going to be horrific? Those are basically our options. And so we're hoping for bad. And exactly where that line is really difficult to say. So again, the consensus in the community is 2 degrees Celsius from pre-industrial temperatures is about what we can tolerate without having truly catastrophic problems. And we're already, getting close to 1 degree. So we're not far away from that. And so the Paris Agreement, is a big step in that direction, but it's not even close to how far we have to go. I don't want to put an exact number on it because it all depends, right? I mean, it's not like, even if the Paris Accord gave us twice as much, we're still going to have big problems going forward no matter what.
And we're getting close to 8 o'clock, and I think 2 more questions. Are you okay?
Sure. Yeah, I'm good.
And I know there is a gentleman here in the front who wants to ask questions for a long time. I was told, yes.
Thanks. Great talk, by the way. I give talks on similar stuff, but as an engineer, I'm also a research engineer. The only question I ask is how much. So our best predictions, how much ocean level rise, how much temperature rise do we expect to see?
Do we expect to see, so those are 2 different questions, temperature rise and sea level rise. So temperature rise is all going to depend on how much we curtail our emissions. I come back to that number, 2 degrees, that's our goal. Again, I oscillate between whether we're going to make it or not, but that's what we have to keep our eye on, is 2 degrees. So that's the answer for temperature. Sea level rise is a little trickier because it's a really slow process. It takes a long time to melt ice. And even if we stopped emitting carbon dioxide today completely, there would still be a lot more warming, which would melt a lot more ice, which would raise the sea level. So no matter what we do, it's going to go up a lot from where it is today. So I think the minimum number this century is going to be a few feet more. 2 feet, say, ballpark. If we don't change things significantly, it's going to be 6 feet or 8 feet or something like that. And you can just look at maps. There are various things online you can look at for how many populated areas end up underwater in that scenario. It's pretty frightening.
And then the last question?
Last question.
Your pick.
Well, I think Chris already picked for me. Let's go back there.
So you talked a little bit about some of the technologies that are forward-looking and possibly scary and may not be good ideas. Are there any that are exciting that we just really haven't been able to explore yet besides solar? And I know space mirrors was one. I don't know what that is. Would like to know more about that.
So I would not dissuade anybody from attempting a solution for this problem as long as it doesn't have significant unintended negative consequences. Putting a mirror in space is so there's 2 different space things I've heard about. One would be that idea of sort of basically reflecting sunlight just out of the way. That would have to be really big, and that would be really expensive. And I don't know, it might just be cheaper to build solar panels. You'd have to do the economics. The other thing is there's actually a solar technology for space where you basically collect the solar energy on satellites and send it as microwaves down to a receiver on Earth where you have a big dish that collects those microwaves and transfers them back into electricity, which is feasible. I think Japan may have been funding a program to explore that for a while now. Maybe that'll work. Again, I think the way the economics of solar energy have changed, it probably is not going to be your cheapest option. And there's people who joke about birds getting cooked as they fly through that beam. Yeah, I mean, again, we need more creative minds thinking about this problem. It is a massive, biggest challenge we've ever faced as a species. And so I sure hope there are some bright minds out there who have ideas that none of us have thought of yet, and they're going to help us solve the problem. All right, that note.
Well, thank you so much, and a big round of applause. Thank you again for the most informative talk. And then if you can hold up your book, As I mentioned in my introduction, Dr. Darling brought some of the copies that you can buy here today from him. A personal thank you to Joe Friedman and again the Alvin H. Baum Family Fund. Thank you everybody for coming. Thank you for your support. Thank you everybody for coming and hope to see you at our next program. Thank you again.